at one example of this process with actual numbers. You'll have in your notes from Thursday of last week. We did this example right here, right? Where we walked through this process of moving the constant over, dividing everything by a, dealing with fractions, yes, but completing the square nonetheless, and then using the square root method to get x by itself, and we got our two answers, and then we said, this can be automated. And so we automated it. We said, all right, let's do it generally. Let's deal with, instead of actual numbers, let's do it A, B, and C. And we hastily sort of ran through this process, and we got to this point right here. Now, what I want to do is a manner of warming up today, since it's been the weekend, it's been a few days probably since your math brain was on, is I'm going to pause our discussion on the quadratic formula, and we're going to talk about some radicals. Mr. Perry next door gave a little test or quiz or whatever, an assessment last week to his honors geometry kids, and it was based on some algebra. And so he came in this morning and told me, man, last week I gave this, these kids stunk it up. They did not remember how to do any of these or many of these radicals. So I thought I might give it to you guys. Y'all have been taught how to do it, and let's see how you do. So this is just going to be a little warm up, and then we'll get back to that. Nate, I know a few of you guys were jotting down our quadratic formula chat. Let's put that on pause. Here's a little warm up for us today. Okay, this isn't a grade or anything like that. This is just going to see if you guys can simplify some radicals. So here we go. Simplify the square root of 324, the square root of 64 times 81, the square root of 8 times 67, and the square root of 72. And then when you are finished with that, to classify the triangle whose sides are given as square root of 7, 10, square root of 93. La 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 la. Do, 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 do. Come on in, George. Do, 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 do. Do, 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 do. And remember, when we're classifying triangles, that's kind of a geometry-ish question, but we're looking for acute, right, or what? Obtuse. Apparently, they're teaching kids these days. My son's in the 4th grade. He said, I can't remember the little song that he sang, but it was about, if the angle's obtuse, then it's got a big caboose. And then he shook his booty. So I don't know how that works, but that's how they're learning it these days, I guess. All right, Georgia, we're doing a little warm up here. So you guys take a couple moments, and then we'll chat about this. Bless you. Y'all need about another minute? Okay. Bah. Is that coming up there? All right, regardless of whether or not you're finished, we're going to start going over these and see how you guys did. Now, the first one should have struck you as a perfect square, right? The wheels should have been turning. We should have recognized 324 as a perfect square. If we did not, that's okay. We can still split it up. You might start small. You might say, 324. It looks like that's a multiple of 4. Maybe I'll quickly divide by 4. Now, that's not the most efficient route. But, you got to start somewhere. What is 324 divided by 4? Am I go that route? Interesting. So if 324 is 81 times 4, then I can split that up as square root of 81 times the square root of 4, which is the same thing as 9 times 2, also known as 18. All right. Thumbs up. Thumbs down. Thumbs kind of sideways. No. All right, number 2. Similarly, we should end up with the square root of 64 times the square root of 81. In other words, 8 times 9, which is 72. What do you think a mistake would look like on number 2? What do you think the wrong way to work this problem would be? Square root of 8 times square root of 9. Okay, so like doing the square root a couple times. What else might be a mistake? Yeah, why would that be tough? Well, we just got through talking about 324 as being a big number, and the way to get around a big number problem is to break it up. Why in the world would I want to take the square root of a huge number when I've already got it split up accordingly, right? So we're being thinkers, not stinkers. Number 3, what should I do to start on number 3? Cancel out the square root. Again, people thinking, oh, let me simplify. It's in the parentheses. Let me simplify some. You might have felt that. Let me simplify square root of 8 and square root of 67 and this, that, and the other. No, man, no. The canceling out of the square and the square root is right up the alley that we've been dealing with in this square root method, is it not? When talking about the square root method, we discussed that those are inverse operations. So this winds up equaling whatever 67 times 8 is. Let's see here. 8 times 6 is 48 and 5 is 53. Did I get 536? Oh, yes, Coach Morgan. Oh, yeah, of course. I got that. That's exactly what I got. Scribble, scribble, scribble. Square root of 72. What do I do with 72? Do you see something hiding in it? Paul, what do you see hiding in 72?
8 and 1.
True that. However, 8 also has 4 and 2. So I got to do a little two-step on that approach. What will be a more efficient way of splitting up 72? 72 is your pretty traditional radicand for this type of problem, Joey. Yeah, 36 and 2. So that winds up being 6 square root of 2. Okay. Now, as far as the one on the right goes, it was a little bit weirder, right? You have to have known a little bit about some acute right and obtuse triangles, and also, consequently, the Pythagorean theorem that goes along with that. What is the Pythagorean theorem, by the way? Who's over there saying that? Joe, louder, please. Anybody agree with Joe? You're all wrong. That's only half of it. Pythagorean theorem says if I've got a right triangle whose legs we might consider calling A and B and whose hypotenuse we call C, then we've got that relationship, that lovely little equation that Joe just hooked us up with, right? A squared plus B squared equals C squared. So it's an if-then statement. And we've talked about that early on in our year, way back in the first semester, okay? But it's been a minute, so we might be a little rusty on Pythagorean theorem. Okay, well, if I were going to plug in A and B and C to check to see if it equals out, then I know I would have a right triangle. In other words, the converse of that, if A squared plus B squared equals C squared, then you got a right triangle whose legs are A and B and whose hypotenuse is C. That's called the converse of the Pythagorean theorem. Ooh, I like how people are taking notes. My goodness. So the going from left to right is the theorem, that's in black. Going from right to left, that's the converse of the theorem. And so what we could do is we could use the converse of the Pythagorean theorem. In other words, we could plug in those 3 values to check to see if it lines up nice and neat. And if it does, great, you got a right triangle. And then if it does not, then you either have an acute triangle or an obtuse triangle, depending upon which way the inequality would go. Okay, and again, this isn't a geometry class, but the check here, the test here, is a test of common sense regarding those 3 numbers. What do I mean by common sense? Well, for a right triangle, what do we know about the lengths of A, B, and C regarding who's the big dog? Who's the biggest? C is the biggest, hypotenuse, right? It should be common sense that the largest side is always across from the largest angle. Did you hear what I said there? The largest side is always across from the largest angle. That's common sense. As my hand spreads out, as my angle gets bigger, my side correspondingly gets bigger. Okay? So of these 3 numbers, A, B, and C, which one is the biggest one? It's always going to be C in the case of a right triangle. Okay? Not necessarily the case with an acute triangle. Definitely the case with an obtuse triangle. Okay? When you got a big caboose, you know you're obtuse, I guess is the way the kids are spinning it these days. So here's my question. What is A, what is B, and what is C in these given sides there? Quentin. Quentin is correct. If you didn't hear what Quentin said, the trick here is that Mr. Perry has lined these up not in ascending order as we usually see things, right? Do y'all remember an easy Pythagorean triple? Somebody call out an easy Pythagorean triple. Y'all haven't learned a Pythagorean triple from me this year. Y'all have forgotten the 3, 4, 5 triangle. 3 squared plus 4 squared equals 5 squared. No? Y'all are making me double question myself here. Let us see. Maybe it's not in chapter 1. Maybe it's not in chapter 2. Y'all telling me we haven't talked about Pythagoras this year? I could have sworn we've talked about Pythagorean theorem. No, not at all. Let's see if I can search this. Pythagorean theorem. Extra stuff, chapter 11. That's not y'all. Maybe we haven't talked about it. Could have sworn we talked about it, Jake. Oh well. Anyway, well, it's coming down the pike then. You know, and I bet maybe it's coming up down here with some quadratic word problems. We'll see. But Quentin is absolutely right that normally speaking, when we see three numbers in the context of the Pythagorean theorem, we see it goes from little to middle to big. And the trick here is that square root of 7 is obviously the smallest number. 10 is the biggest number. How do I know that? How can I quickly compare 10 and the square root of 93? You dadgum right it is, Nate. 10 is the square root of 100. So if I were going to plug these in, if I were going to check, what's the square root of 7 squared? What's the square root of 93 squared? And does that equal 10 squared? You bet your biscuits it does. So what kind of triangle is this? A right triangle. Okay? The mistake that we would make would be to say, what's the square root of 7 squared? 7. What's the square root of 10? Or excuse me, what is 10 squared? 100. Add those together, you get 107. And then the geometry student thinks, 107 is greater than 93 squared or 93 squared. Therefore, this one must be acute. And they say, because the C is not big enough, so it's too small, it must be acute. And then they get that wrong because they don't understand the simple common sense ordering of numbers such as these. All right, so anyway, he and I were talking about that earlier today. I thought, man, I'm gonna share that with my 8th graders, just give them a kind of a preview of sort of some algebra that comes up in geometry, right? Some algebra that comes up in geometry. Now, we said last time that we met, we went through the Pythagorean, or excuse me, the quadratic formula, and we derived it. And I told you guys, please, 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 pretty please, with a cherry on top, nay, with 2 cherries on top, memorize what's in the boxes. Said memorize what's in the boxes, okay? You ought to be able to quote the quadratic formula from memory once you're out of Algebra 1. Anybody that has taken Algebra 1 ought to successfully be able to quote what's up on the screen there in those 2 orange boxes, okay? Given that ax squared plus bx plus c equals 0, where a does not equal 0, then the 2 solutions to that equation will be, and will always be, x equals the opposite of b, plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, that is a verbatim quote of what is in those 2 boxes. Now, I want to focus in with the time that we have left today on the radicand. In other words, b squared minus 4ac. Okay, that goes by a special name that you want to understand. That name is the discriminant. Write that down, the discriminant. The radicand of our quadratic formula, b squared minus 4ac, can tell us a lot about the equation that we're trying to solve, and consequently the shape of the parabola whose equation we're trying to solve. Okay, if b squared minus 4ac, called our discriminant, we can say, just for shorthand's sake, let's call that d. If we find that the discriminant is greater than 0, that's my first case, then I know I'm going to have two distinct real roots. That's where the parabola hits the x-axis in two places, two unique, distinct places. Okay? If the discriminant is a perfect square, in other words, we've got the square root of like 81 or the square root of 64, the radical is going to go away, and our solutions are going to be rational numbers, and that means that they can be expressed as a ratio of integers. Just a little reminder there in the parentheses. If the discriminant is not a perfect square, then we're going to have a couple of irrational answers. Now, you and I have seen both of those types of examples flesh out in the last week or so. Okay, when you're done taking these notes down, I'll show you what I mean. The second scenario that we find ourselves in is, okay, well, what if the discriminant equals 0? In other words, what if, yeah, the radical goes away, but that whole term goes away. So instead of the opposite of b plus or minus the square root of all that, I've just got the opposite of b plus or minus 0. Well, plus 0 and minus 0, there's no difference. So I would literally, my two answers would be the opposite of b over 2a. That's a double root or a repeated root. And that repeated root would be x equals the opposite of b over 2a. Now, that ought to ring a bell. Who remembers having seen somewhere in our Algebra 1 class this year, unlike the Pythagorean Theorem, I know we've done this, the opposite of b over 2a? In which context have you seen that? Ooh, this is going in the Wayback Machine. Take a stab, Jake. Not slope. That's not a bad guess. Luke? Not perfect square. Jack?
Linear equations.
Not linear equations. Remember, what are we dealing with? What shape are we dealing with when we're solving quadratics? A parabola. It has to do with parabolas. What about a parabola has negative or the opposite of b over 2a? That is the x-coordinate of the vertex. And if you remember that in this scenario where we've got two repeated roots, that graphically speaking, that's like where my parabola is going to be sitting on, that was a lousy parabola. Let's try that again. It's going to be sitting on the x-axis. In other words, the point that it has in contact with the x-axis, the one and only one root or 0, okay, is the vertex. And that vertex, we already know, is going to have an x-coordinate of the opposite of b over 2a, and the y-coordinate is going to be 0. So that's the scenario where we're talking about if the discriminant equals 0, then that parabola is tangent to the x-axis. Okay? And then guess what? If the discriminant is less than 0, what's another way of saying less than 0? Negative. If the discriminant is negative, you've got a negative radicand, and at this point you're like, ruh-roh, can't handle that. Okay? That's because there's not going to be any real solutions. There are no real x values. There are no real numbers that would make that a true statement. We're going to have two complex, or what you'll learn to call imaginary solutions. Okay, so graphically speaking, here's what that would look like. That would be just where, you know, the parabola doesn't touch the x-axis. Up here at that first scenario, that was where the parabola hit the x-axis in two distinct places, right? So in other words, we've got two roots. We've got one root, and we got no roots. That's an oversimplification of it, but the idea is, as far as x-intercepts go, that's what we're talking about there, okay? So two distinct real roots, two repeated roots, we would just consider it to be one number, and then there's no real roots because it doesn't hit the x-axis, or no x-intercepts will probably be a better way of describing that, all right? So the discriminant can tell us a lot about the curve and the number and the nature of the roots of that curve. Okay, the number and the nature of the roots of that curve. Let's look at an example now, and let's before we do anything, let's analyze the discriminant. Okay. George, quote for me what the discriminant is, letter-wise. Perfect. B squared minus 4AC. So very quickly, I can determine the number and the nature of the roots by looking at the discriminant, B squared minus 4AC. All right, Andrew, what's B?
6.
Try again.
-6.
-6, good. So B squared would be 36 in this case. And then let's see here. Charlie, what's A? And Charlie, what's C? -7. Perfect. Did you notice I pressed Andrew and then Charlie did it well to include the what with the A, B, and C? Include the signage. If it's positive, it's positive. If it's negative, it's negative. That needs to be there. All right, now let's see here. That's going to be 36 and 28. So that's 64. All right. Now, what can you tell me then about the number and the nature of the roots of this equation without even having solved anything? I haven't factored. I haven't tried completing the square or anything. Jack. 2 rational roots. They're different, they're distinct, but there's 2 rational roots here. Okay? And we knew that just by doing a real quick, simple calculation of B squared minus 4AC. That's powerful. That means that if I'm going through the process, whether it's factoring in the ZPP in this case, or graphing, or completing the square in the quadratic form, whatever method I approach this problem on, I already know that I should get 2 rational numbers as my answers. That's a good self-check. Okay, that's a good self-check. We won't have time to do all of these, but let's start with graphing. Let's start with graphing. Okay. Tiago, is this parabola going to be concave up or concave down, or do we know? Okay, Grove, do you know? Concave up or concave down?
Concave up.
How do you know?
Positive number, and there's going to be
The leading coefficient is positive, and we know that there's going to be 2 distinct real roots. So we already know that this parabola is going to kind of look like this, right? We know the x-axis is going to be there. So really, it's just now a matter of figuring out where the other part of it goes, okay? So like we know that we're hunting for these 2 numbers. We'll call this R1 for root 1, and we'll call this R2 for root 2. That's your job. Your job is to find those 2 x-intercepts. Okay. What about the y-intercept? Jack, Candiato, how could I go about finding a y-intercept? What do you know about every point on the y-axis? What do they all have in common? They all have an x value of, louder. Yeah, buddy. They've all got an x coordinate of 0. In other words, consider this to be the quadratic function f of x equals x squared minus 6x minus 7. All right, and real quickly, we just want to analyze what is f of 0. In other words, what is the y value when x equals 0? Okay, so that's going to be where I've got my first 2 terms. I like to do the cover-up principle because plugging in x equals 0 goes away, so I've got a y-intercept of -7. So back on my graph now, there's -7. 1, 2, 3, 4, 5, 6, 7. All right, and we're out of time for today. We'll have to pick up with more of this tomorrow. All right, you guys, I hope you had a good class today. I know I did. Work hard for me if you haven't done any Delta Math in a while, which very few of you guys have actually been doing your homework. So get some of that done, and I will see y'all tomorrow. Live Jesus in our hearts. All right, fellas, thank you so much. Y'all enjoy your day. It's supposed to be a beautiful one.